Let's go ahead with our last concern with variation of parameters, which is how we might solve higher order variation of parameter problems. So we can use this method for higher order ODEs. We showed the example for second order, but if we have a set of fundamental solutions y1 through yn, to the homogeneous problem, then if we want to find particular solutions to a differential equation that looks like nth derivative plus a function times the n minus 1th derivative, so on and so forth until a function times the first derivative and a function times just y itself. If all that's equal to some function f to make this a non-homogeneous problem, we can use variation of parameters as long as we have that fundamental solution set. It's just going to introduce like bigger and bigger sets of equations we have to solve, so bigger and bigger determinants of functions that we evaluate, basically. So the solutions are given by y sub p is equal to u1 y1 plus u2 y2, all the way down through that nth solution in your fundamental solution set, where the derivative of each u is given by some wk over w. And w is the Wronskian, same as before. And WK is going to follow the same rule as those two other matrices we built in our 2x2 example. It's going to take away one of the columns. And it's going to replace it with something that's all 0 and then puts f at the very bottom. And I'm going to tell you that you can do it for any order, but I'm only going to show you third order, because at that point even the determinants are too big. Somebody who's not taken linear algebra won't be super comfortable using it. But I need the next slide to do that, so please pause if you're still writing, and then I will write out those determinants for you. So, for example, if you wanted to see this for third order, our problem would be that we have y triple prime plus p2 y double prime plus p1 y prime plus p0 times y is equal to f. Then our w is y1, y2, y3 along the top, and we take derivatives down until we have a square. y1 prime, y1 double prime, y2 prime, y2 double prime, and y3 prime, y3 double prime. And remember, we build this with solutions to the homogeneous problem. So for y1, y2, y3, solutions to the homogeneous ODE, y triple prime plus p2 y double prime plus p1 y plus p0, p y prime plus p0 y equal to 0. So this is the same way that you would have checked fundamental solution sets for a third order equation. It's still that exact same Wronskian. And then building, oops, not ready for my U's yet. Building my W1, what I would do is I would replace my first column with 0, 0, F, but then copy W otherwise. Then to build my W2, I would start copying W, but then I would replace the second column with that 0, 0, F, and then I would go back to following what W was. And same pattern for W3. I'm going to copy the first two columns of W, and then my last column, the third one, will be 0, 0, F. Oops, I'm not making matrices, I'm making determinants. And you would have to evaluate all those determinants. If you don't know how to take a 3 by 3 determinant, you would have to figure that out. But once you did, U1 prime is W1 over W, U2 prime is W2 over W, and U3 prime is W3 over W. And we would have to integrate those to get U1, U2, U3. But then the particular solution is going to be y sub p equal to U1, Y1 plus U2, Y2 plus U3, Y3. So hopefully it feels really similar to the examples we were doing with only second order. There's just more functions that you have to include. We won't actually work with this because this is too long a problem to give you like on an exam. But I hope it's helpful to know that this method is a bit more general than it seemed to be at the start of the lecture videos. So that's it for variation of parameters. I will see you in the next set of videos.